Hi, this is Mark Kemper with EMS. In this video we're going to demonstrate the Zeiss Comet L3D 2 3D scanner. This is a projected light using a blue LED non-contact 3D scanner. Typically it's going to be used for reverse engineering and inspection applications. So what we'll do today is we'll go through and kind of show you the features of the scanner, how it works. We'll actually scan a sample part that you see here, walk you through a little bit of the software and how that all works, and then we'll talk about how it's used in downstream applications for things like reverse engineering and inspection. So let's get started by taking a closer look at the actual scanner. So the first thing you probably notice about the new Comet L3D 2, which is the newest version of the Comet scanner, is the new size. It's much more compact. It's about 4 inches tall by about 8 inches by about 16 inches long. So sizes come down, and that just makes it more portable, more compact, because people do take these out on the shop floor or into other environments or travel with it. So having that smaller size is really nice. And then basically what you have here is the lens and then the projector, and I'll talk more about that here in a second. As far as mounting the scanner, you can see here I have it on what we call a measurement stand. That's a very nice rigid setup, which is nice for inspection because while we're scanning we want everything to be very still. So having it on a rigid setup like that really gets us down to that that low micrometer accuracy that we're looking for. So you can see the small size. You've got the handle on here, and you can also mount it on a tripod. People put it on a jib arm, different things. Key thing is just it's not moving while it's scanning. But back to the lenses here and the projector. So what's really nice about this system is the lenses and the projector are interchangeable. They basically come in a set like this, and you change them out. So why you do that is because it allows you to scan a whole variety of sizes of parts. Everything down to a small part you could barely see in your hand all the way to a complete automobile you could scan with this system. And what you do is you select the lens choice that you want and put it in the system. So it starts at a 45 millimeter field of view, a 75, a 100, a 250, and a 500. So that's basically how large of an area the scanner can see while it's scanning. So if you were doing, let's say, a small coin like a dime, you could put that 45 millimeter lens in, and that's going to give you 18 micron point spacing. Okay, if you put the 500 micron in, you're going to get about 169 micron point spacing. So the sensor is a 5 megapixel sensor, meaning 5 million points per scan. The different lens choices is just how you kind of squeeze those points together. So smaller lens, you're going to get very dense points. That's going to allow you to pick up a lot of detail. So you just simply change them out, recalibrate the system, which is very fast. It's just a plate. You take some measurements and it recalibrates for those lenses, and then you do your scanning, which we'll show here in a minute. But basically it's a blue projector here, and it projects out a light pattern. It's also called white light scanning because traditionally they were white halogen lights. Now everything is blue LED light. And it's called fringe pattern, it's called structured pattern, whatever you want to call it, but it puts out a bar pattern starting with some large bars. They get smaller and then they shift across the part, and it's a process called triangulation, which we'll get into more when we actually scan the part. But pretty basic setup. You've got a cable that goes to the PC and the power to get the data and obviously power to the unit. All plugs right in. You can see we're using a laptop here. So we'll set up and actually do some scanning, but very easy to change the lenses, very compact in size, easy to mount, and you're ready to scan. So next, why don't we actually do a little bit of scanning and we'll talk about that process. Okay, so now we're ready to actually do some scanning, and basically what I do is I set up the scanner because it's all line of sight, and usually what I want to do is kind of angle down. And you see that little X on the screen, that kind of tells me I'm in the center of the part. You can't see it, but there's a little laser there, 2 little laser points. Once they align right next to each other, you know you're at the right standoff distance, because again there is a focal range here, a depth of field. So we have the 500 millimeter lens in here, so you can kind of see how big of an area we can scan in a single scan. And the wider the lens, the deeper the depth of field, which is kind of standard photography thinking. If you think about this, it's almost like a photography system when we get into different settings on the scanner. So we've got a nice deep depth of field. I've centered the part in there. And we've got a little preview here on the screen. But the reason why I want to angle down is because if you were to just scan a part straight on, you're not going to get, like if this was a rib or something and you scan straight on, you're not going to get the sides very well, or maybe even the top. So surfaces that are perpendicular just wouldn't scan well. So what we typically do is we will aim the scanner down and take a series of scans. This is sitting on a rotary table here that's going to automatically rotate for us, and index around based on what we tell it. And that's kind of driven by just the part geometry. If it's got a lot of detail, I will set that higher, meaning more increments, so we can pick up all the data. Because again, everything is line of sight. If it can't see it, it won't scan it. So we'll take a series of scans pointing down, and then we'll either slide the scanner down and point up. That's kind of why you see I have the part this way. Or we'll just simply flip the part over and leave the scanner where it is and scan down. And we'll take those two data sets and then align them and merge them. So you're always taking, you know, multiple scans, typically 2 setups to scan a part. Now I could just set the part on the table and scan it and flip it over and do it that way, but I like to fixture it up. It just gives me cleaner scan. I don't pick up the table, even though that's easy to do in the software. Speaking of software, this is the new Comet L3D software that comes with the scanner. And with this new system, it's greatly improved. It's more automated. Really nice software for the user. Really walks you through the process. So why don't we go ahead and get it started scanning, and then we can continue to talk about it. So I've already told it. I've just clicked that I want to do a rotary scan. Then I hit next. And it's going to start scanning. Now, what you didn't see me do here, there's a slider adjuster for the exposure rate, and you just kind of move that up and down. If the part gets red, you've overexposed it. If it gets too dark, you've underexposed it. So you just slide that along until you get it to where you want it, and then scan. If you do it, what that's going to do is you're just either not going to get data or you're going to overexpose it, which won't give you data, and if you underexpose, you won't get data. So what I have here is 2 scans, and then I'm going to come in here and we'll zoom these up. And then what I want to do is just pick a few common points. And you'll start to see the data line up. And we can zoom up here. Okay? And what we're trying to do is just give it a couple of points to find the center of the table, the rotary table. Because the scanner doesn't know, we could have moved the scanner around, moved the rotary table around. In order for us to automatically align all of those scans as you see it doing here, it needs to know where the center of the table is. So by taking a scan and then rotating and then taking a scan and then aligning those two, the software can then calculate where the center of that table is. Okay? So let's zoom this out so you can kind of see, and we can kind of rotate and zoom. So what you're going to start seeing is these scans stack up on each other, and they should come in pretty well aligned. We will do a final alignment when we're done, but this should be pretty close. You want them close so when you do that fine-tune alignment at the very end, it doesn't have to search so far, because we're going to be collecting theoretically up to 5 million points per scan. Now normally, unless you're scanning the entire view of the lens, we may only be getting, let's say, 1 million points here because it's what it picks up. But potentially every scan could have 5 million points. So you can have some very large data sets when you get into this high resolution scanning. But as you can see, it's going to pick up a really, really fine detail on this part. So it's basically projecting that light pattern, and then picking it up with the lens and then moving along and scanning. So you can see it happens very fast. Each scan only takes a few seconds. We'll zoom in here in a minute. You can see the actual light pattern. But that pattern just shifts across the part. The lens is picking it up through that process of triangulation and then moving on to the next one. So you can see a setup like this really only takes a minute or two. You go anywhere. We're doing 10 rotations here, so every 36 degrees. Probably the lowest we go is maybe down to about every 10 degrees, so 36. But that's kind of extreme cases, okay? So you can see here we have all of our scans. They've all lined up quite nicely, and we can rotate it around. But you can see there's areas of the part we just didn't reach. That's on the top side, so that would be up underneath the part here. It can't see it. That's the reason we're going to flip this over, scan it again, and put those two data sets together. And we'll zoom in on the next scan so you can see it. So I'm going to go ahead and flip the part over, and then we'll start it again. Okay, so now we're ready to go ahead. We flipped the part over, and we're zoomed up here so you can kind of see it. And we're going to go ahead and tell it to go ahead and scan. So it's going to take that first scan and maybe able to see that light pattern shift across the part. It's going to rotate. You'll see the next one. So again, it's just projecting that pattern, and then anywhere that lens can see the pattern, it's going to pick that up. So as those bars distort across the shape, that's where it gets the 3D shape. So it's looking at the edge of that bar. Okay, and again, you can see how quick it'll scan. So basically, if the projector, if the lens can see where the projected light is, it should pick it up, as long as, again, it's in that depth of field. And how you fixture the parts, as I mentioned earlier, is completely up to you. You can see here I've just got a simple fixture. As long as when it's scanning, it's not moving, the part isn't moving, and the scanner itself isn't moving, then you're fine. You'll get good quality data. If not, it's going to have, you'll see basically ripples in it where it was moving around. So it's only important during that quick scanning process that everything is still. In between scans, obviously it has to rotate, and you might be able to see the lasers there. That's where I mentioned earlier, where we use that to line up to set the depth of field. So when those two laser lights are real close together, right now they're literally on top of each other. That's how you know you've got your right depth of field. Okay, and again, this has a pretty big depth of field of probably about 8 inches or so. So as long as you're somewhat centered on those two laser lights, you're fine. So that's really the process. It's just rotate, scan, rotate, scan. And we'll talk here in a minute about other methods besides just using the rotary table. There are other methods to scan parts. Okay, so now that our second set of scans are done, we had flipped the part, we had taken those scans. The last thing we'll do is align those two data sets. Okay, so similar to the window that came up before for the alignment of the initial two scans, we're going to do the same thing with the two sets of scan data here. So what I want to do is get them in a, I like to get them in a view that's similar, same orientation, and you can see the data is missing more on the one scan than the other. Again, that's the line of sight issue. And I'm just kind of picking some common points to get them close. And then once I get it there, I'll go ahead and hit next. And then it will align all of those scans. So that now that I have those two sets of scans, 10 in each set, so 20 scans total aligned. And then the last step is to actually post-process it. So we'll go ahead and do that next. We'll actually post-process the data and turn it into an STL file. Okay, so the last step, as I mentioned, was the post-process, and we'll go ahead and hit start. And what that's going to do is take all of those scans and merge them together, because right now they're just a bunch of point clouds. So like I said, there's 20 of them. They're individual point cloud files. We want to merge them all together and make a polygon mesh, which is an STL file. And there's some real advantages to having that as a polygon mesh. We'll talk about that for our downstream applications. But instead of a bunch of points, now I've got polys. So it aligns all those data sets together. You can see I've got some floating data out there I can easily delete. You can see where I had the fixture point on there, but you can see the scan data. So in a minute, we'll take a closer look at the scan data. Last thing I wanted to talk about, we'll show here in a second, is using targets instead of the rotary table. Okay, so there's many methods to scanning and aligning the data. The one we showed here was the rotary, and this table will actually hold quite heavy weight, up to a couple hundred pounds. The rotary table will hold. The problem is some parts are just too big. We talked about scanning a car. Obviously, you can't get a car on this table. So how do you scan and move around and align? Well, there's a couple ways to do it. One of them being targets. You randomly place these targets on the part, and then basically you take a scan, you move over, you take another scan, move over, take another scan. And as you move over, you just need to have some of the overlapping targets from the first scan. So if we took a scan here and then moved over, I need to have at least 3 of those targets from the first scan in the second scan, and then it can align them. Okay, so that's called target registration. The advantage of that is when let's say you were going down the side of a car, it's a very nondescript surface. It would be very easy for the data to slide around. So the random placing of the targets gives it something to lock onto. The other way is if you had no targets, a part like this we could still scan with just feature recognition. So if I scanned right here, there's a lot of features, and if I move down and scan again, that principle of overlapping data, just like the overlapping targets, there's enough discrete, unique data here that it would be able to line it up. Where if I were to try to go along this flat table, there's no way for the 2 scans to line up very well. Even with the holes, the hole pattern on this table is even, so it would get confused. So you can just do feature-based alignment, part features. You can do target alignment. And then you can also do the rotary table alignment. So small parts you're going to do with that. Bigger parts that you can't easily either put on a rotary or just or outside the field of view, you might use target or just again the feature. The last thing you can use is photogrammetry. We won't go into that in this video, but that allows you to do high accuracy on very large parts. So just to wrap up this video, the new Comet L3D 2, high accuracy, high resolution, high detail. We can get accuracy down into the 20, even closer down to 10 microns on small parts. So we can get into very high accuracy, down to 18 micron point spacing, do a variety of parts from very small to very large. You've got the interchangeable lenses. It's a portable system. So a very nice system to do both reverse engineering and inspection. So last thing is we'll take a look at this part. We'll kind of again the throttle body we scanned. We'll take a look at that and show you again, discuss some of those downstream applications.
Okay, lastly here we want to talk about the downstream applications you can use the scan data for. So first let's just take a look. We're working here in Design X by Geomagics, and this is a reverse engineering software product that allows you to take the scan data and build a solid or surface model from the data, because most CAD systems cannot work with this scan data, unfortunately. So you need a third-party product like this. So if you take a look here, this is the scan data from the Zeiss system, and we'll just zoom in and you can see the level of detail. You can see the parting line here. You can see like some flash on the part. This part was cast, so you can just see how detailed it is. Now, again, there's certain areas the scanner just can't see down into. You see an area there, maybe in a couple of these areas, but a lot of those areas aren't critical. We have enough information to probably guess at it, but all the critical stuff is here. You can even see the part number. And this throttle body has a very complex shape in here, this transition area. So this is the raw scan data, and very similar to how you would create a CAD file in a normal solid modeling system is really the same way it was done here. It's just a matter of extracting information from the scan data and then actually building features. So if you kind of walk down through this tree, you can kind of see how it was done. So there's no automatic 3D scan button you hit. It's a matter of extracting sections and then lofting, extruding, you know, doing different things all the way through. So you can see this entire process. And then basically what you end up with is a feature-based CAD model. And this, what again was key, is this transition area here, and having the scan data allowed us to very accurately scan that or design this area, which would have been very difficult to do by hand. The other neat thing is, as you're designing your solid model, you can always be checking back to your scan data. So we're running a deviation analysis here on the solid model, and we'll compare it. So you can see in this throttle body, this green area is very, very accurate to the part. Also, a lot of these machine surfaces are very accurate because they're critical. And then there's other areas that maybe aren't as critical. You notice here on the bottom that part of it is green, and then you can see here it turns into a teal, which if you look over here, that's outside of our tolerance range. So what that tells us is we modeled this area flat, but the actual part we scanned probably wasn't flat. So when you model things from scan data, you typically want to model it as it was designed and not as it's manufactured. So that tells us this part is not quite flat from the manufacturing process. So when we designed it or reverse engineered it, we did make it flat, and that's why you see the difference here. But you get those options as you're designing. You can make those decisions as you go along. So that's called the accuracy analyzer, and it kind of gives us that colored heat map showing us where we're plus or minus, or if it's within green and whatever tolerance we set, you know, tells us our part is good. So ultimately, this is what we end up with. This is a CAD model. This now can be output as an IGES, a step, or a parasolid, where the scan data, let's turn this solid model back off, is an exact replica of the manufactured part, and it's just polygons. It is not a CAD model, so you really can't do anything with this as far as downstream manufacturing or assembly or other processes you're going to do. You can look at this, but you have to go through this process of converting it or building CAD data from it. And again, that is not a push button. You know, a part like this could easily take a day to reverse engineer, you know, half a day to a day, depending on the operator and their skill level. So that's a big use of scan data, is the reverse engineering. And then the other thing is being able to do inspection. So basically scanning the part and comparing it to existing CAD. So let's show that next. So what I'm going to do is I'm going to pull up an inspection report. This was done in Polyworks, which is a very powerful inspection software product. So you would import the scan data into Polyworks. You would import the nominal CAD file, and then you would do the comparison between the two. So there's your nominal CAD. Here's our scan data, and same kind of thing we showed in reverse engineering is that heat map, and we're looking at the accuracy of it. Okay, so you can see what that report looks like, and then we can do very specific GD&T callouts. The heat map is nice, but really doesn't give you a lot of very specific information. So now we can check things. So we can do a datum alignment. So it's just like you would do on a CMM, except we 3D scan the part in a non-contact sense. We select our datum alignment system, and then we do different measurements. So we can do a roundness, we can do position, we can do flatness, all your standard GD&T callouts. We could do bolt patterns. So you see here's a flatness callout. We put the allowable deviation, and then if the part is, you know, within that deviation. So you can see these different callouts, how they reference different datums, and if it passes or fails, what the nominal is, what it actually measures, what the tolerance is, and then what the deviation is. So you can do full-blown inspection reports by taking that scan data and importing it, like I said, into a product like SolidWorks. So here's some more callouts. So you just build your inspection report based off your drawing, and you may scan 10 different parts you could automatically have the Polyworks software automatically import each set of scan data, run the report, save the report, and you can save the report as a PDF. You can save it as an Excel spreadsheet. Different methods so that you can use the data for other downstream applications. But you basically run an inspection report on each part to see if it passes or fails. This is a nice feature where you can cut sections through the part, and then you get color coding as well. So we call these a whisker plot. A little bit hard to see here, but these whiskers represent if for those different sections cut. You can see the different, again, gradients. Yellow would be going out of tolerance towards red one way, and then blue towards purple the other way. So you can actually cut sections through the part and take a look at it. So you got some very powerful inspection features here with Polyworks. So just to kind of wrap up this video, the Zeiss new Comet system, the L3D2, gives you all those different lens choices, allows you to scan small to large parts, and then you can take that scan data into downstream applications either for reverse engineering or for inspection, as you see here.